All right, welcome everybody. Today we're going to talk about Calc Lesson number 75. This is the beginning of our final chapter 7, and today we're going to talk about section 7.1, the area of a region between two curves, and please note that this is only day 1. When it comes to chapter 7, there's good news and there's bad news. The bad news is that these sections are generally considered to be some of the most challenging in calculus, which should make sense because they're the last chapter, but there's lots of good news as well. The first of which is that there is a immediate connection between some of this new stuff and some of the old stuff that you were quite good at. And the other good news is that in a normal year, you would be required to create all these graphs for yourself and find all the points of intersection. But in a way, for us to kind of make it much easier and much less painful for you, we're going to give you all the graphs ahead of time, give you all the points of intersection, which is going to make your life infinitely easier. So take a look here at number 1. For y equals x squared, find the area under the curve between x equals 0, x equals 2, and y equals 0. When you see those words, area under the curve, you should hopefully think back to the very beginning, chapter 4, integration. We found a whole bunch of area under the curve, and let's make sure we remember how to do that. First of all, let's go ahead and highlight the region that we're talking about. So notice here that in the graph, we have for you, of course, x squared. That's the quadratic that goes through 0, 0, 1, 1, 2, 4. Then notice I have two vertical lines, x equals 0 and x equals 2. And then, of course, y equals 0 is the x-axis. So what we're really talking about when we're talking about the area under the curve is that yellow shaded region right there. Hopefully you remember back from chapter 4 that the way that you can find that area under the curve is by doing an integration. So the area would be equal to the integration. You're talking about integrating x's, so you're going to say from what starting x of the shaded region to what ending x of the shaded region. So hopefully you agree that that is from 0 to 2. So those are my lower and upper limits of integration. What is it that I'm integrating? X squared, and you should, of course, follow it with a dx. Again, we've been integrating much more difficult things, but how do you integrate something simple like x squared? You would raise it to the 1 higher power, divided by that power. Then you would evaluate it from 0 to 2. Remember, that's the fundamental theorem of calculus. You would plug the top number in first, which would be 2. So that would give you 2 cubed over 3. Then remember, you always subtract. That's what the fundamental theorem of calculus says. Then you plug in the bottom number. When you go ahead and calculate, so 2 cubed is 8 thirds minus 0, which means your final answer for the area under the curve, that shaded region, is in fact 8 thirds. So again, those are the types of problems we did when we first started integration. Hopefully it's familiar and it makes sense. Here's the thing that you actually might not have been aware of. So what you actually found is not just the area under the curve x squared, but what you actually found is the area. So this is actually the area between two curves. And those two curves are y1 equals x squared, and y2 is just y equals 0, which is the x-axis. So basically what you really did is you took y1 minus y2 because it was x squared minus just 0. That's why it still wound up being x squared. But the key point here is that you didn't just find the area under a curve. You actually found the area between two curves. And that's really what the whole point of the next couple of lessons is. So how do you know which curves you're dealing with? How do you know what to actually do with it? Well, take a look below here. So if the bottom curve was not y equals 0, you would have had to actually subtract the functions before integrating. As I mentioned above there, if we had subtracted, because of the fact that you were just subtracting 0, it wouldn't have mattered. So the fact that we didn't was fine. But if the bottom curve is not 0, you have to actually subtract before you integrate. Well, how do you know what to subtract? Well, here's the formula. If you're ever trying to find the area between two curves, you're going to find the integration from a to b of f minus g, where f always has to be the top curve and g always has to be the bottom curve. So generally speaking, you're doing top minus bottom. And then very important, note that the top curve and the bottom curve can switch throughout the interval. So you do have to be very careful. This should hopefully make a lot of sense once we take a look here at number 2. So find the area bounded by y equals x squared plus 2. That is the parabola, which you can see is the dotted graph in green. Y equals negative x. That is the line with a negative slope in blue. X equals 0 is in red, and x equals 1 is in purple. So again, normally in a normal year, you would have to graph all these for yourself. You would have to find all those points of intersection, but our gift to you to try to make it much easier is we're going to do it for you. All you have to do to start is go ahead and highlight that region. So you are looking for the region that is bounded by those 4 curves. So again, as I highlight the region on mine, you should highlight the region on yours as well. And then if you're trying to find the area between 2 curves, and you're trying to do it if the problem is all in terms of x's, which it will be for today, you're always going to do the top curve minus the bottom curve. Literally, whichever curve is higher minus whatever curve is lower. So as I go to set up this problem, I'm going to be talking about the fact that the area is equal to the integration of the starting x for the region to the ending x. So that would be from 0 to 1. Then again, you have to do the top curve minus the bottom curve. Hopefully you would agree that for that entire region, the top curve is always the green dash line, where the bottom curve is always the line. So the top and the bottom do not switch between this, which makes it much easier to calculate. So you're going to find the integration from 0 to 1 of the top curve, which is x squared plus 2, minus the bottom curve, which is negative x. And then that entire thing should be dx'd. So before you integrate, again, let's just simplify. So this becomes the integration from 0 to 1 of x squared plus x plus 2. And again, I still have the integration symbol because all I did so far was simplify. Now I'm going to go ahead and integrate each one at a time. So x squared becomes x cubed over 3 plus x squared over 2 plus 2x. I'm going to go ahead and evaluate that from 0 to 1. I'm going to start by plugging in the 1, which is going to give me 1/3 plus 1/2 plus 2 minus, nice and easy. If you plug a 0 in for all of those, that is going to cancel. Here is where it would be fine to have a fraction or a decimal. If you were going to try to find a fraction, you would find a common denominator, which would be 6. So this would be 2 plus 3 plus 12, which would give you a total of 17/6. And again, if you wanted to find the decimal approximation, that would be fine as well. So if the graph is already made for you, which I've already told you it will be, then it should be very simple to just simply identify the top minus the bottom and then go ahead and integrate as per usual. Let's go ahead and take a look here at number 3. So again, you're being asked to find the area between the 2 graphs here. You have the quadratic in blue and you have the line in red. Now, obviously, even though we're making the graphs for you, we would hope that you would be able to distinguish between which graph was which. So that is obviously something that you should be sure of. And again, something to point out, so these points of intersection, if you were going to find those points of intersection algebraically, you would have to set these 2 equations equal to each other, put them on the same side, set it equal to 0, factor and solve. But again, we're solving you all that work. We're saving you all that work, rather, so you're welcome. Let's go ahead and again, you should always highlight the region in question. That we're not going to do for you, so we do want to make sure that you can at least do that part. So here is what I'm looking for. Again, for today, you're always doing top minus bottom. And again, hopefully you would agree that throughout the entire region here, your top curve is always the red one, where your bottom curve is always the blue one. And again, you could kind of just draw lines from the top curve to the bottom curve if you're having any trouble distinguishing between the two. So you're going to go ahead and set up your area as the integration. And again, it's from the starting region of the x to the ending x. So that would be from -2 to 2. You're going to do the top curve, which is the line, so 2x plus 5, minus the bottom curve, which is the quadratic, x squared plus 2x plus 1. Then you're going to simply go ahead and simplify. So as you simplify, that means you're going to distribute this minus and then just kind of put it in the correct order. So when you do that, you're going to get a negative x squared. Turns out that the x's are actually going to cancel, and you're going to just be left with negative x squared plus 4. And again, that should be dx, or whatever the variable happens to be. So now you're free to integrate. So this is going to become negative x to the third over 3 plus 4x. And you're going to evaluate that from negative 2 to 2. Not quite as simple as the previous one because you do have to actually evaluate both. So as I go ahead and start with the 2, that is going to give me negative 8 thirds plus 8. Then remember, it's always a minus. So if you cube a negative 2, you're going to get a negative 8, which is then going to be made negative again. So that's going to be a positive 8 thirds minus 8. So once you're to here, again, there's lots of different ways you can calculate it. You can plug it into your calculator. You can find a common denominator. For me, I know that I'm going to think about it as distributing this minus. So I'm going to wind up with negative 8 thirds minus 8 thirds, which is negative 16 thirds. Then I'm going to wind up with 8 plus 8, which is plus 16. If I go ahead and think of this as a common denominator, negative 16 thirds plus 48 thirds is going to wind up giving me my final answer of 32 thirds. And again, the decimal equivalent would also be fine. If you would prefer to do that, you can use your calculator to assist you. So if you're wondering to yourself, okay, does this get harder? The truth for today is not by much. The first way that it gets harder is here in number 4. So again, notice you're trying to find the area between a cubic and a quadratic. So my cubic is there in blue, and then my quadratic is there in green. And again, think about if you were asked to kind of graph these from scratch, that would require you to remember all the rules about end behavior and multiplicity, how to find the vertex and the x-intercepts. We've kind of done all that for you, and we see that these two graphs meet at 3 different locations, all of which are pointed out here. So if we're trying to find the area between the graphs, you have to be a little bit careful here. There are actually kind of 2 different regions. I'm going to go ahead and first show you one in yellow. So here is the first region that is between the blue curve and the green curve. And then there's a second region, and that would be here. Now, technically, this is also between the 2 curves, but the reason why I'm doing it in a different color is because if you take a look here, you should hopefully agree that the top and the bottom are switching. So let's pay extra attention to these points of intersection because wherever those x values are, that's going to be important as I go to set up my integration. So looking at the yellow shading, the top graph is the blue, and then the bottom graph is the green. Once I actually hit 0, 0, it switches. So my top curve now becomes the green, and my bottom curve now becomes the blue. So not a big deal, pretty easy to see visually. It just means a little bit more work in your integration because you have to separate your calculations. And again, we did this back in chapter 4. Shouldn't be a huge deal, but again, it's just slightly more work, but I think we can handle it. So we're going to go ahead and start by doing the yellow piece. So the yellow piece is going to be the integration from negative 2 to 0 because again, those are the x values. Here, we're going to do top minus bottom. So the top curve is going to be the 3x cubed minus x squared minus 10x. And then minus the bottom curve, which is going to be negative x squared plus 2x. And again, that whole thing really should be dx. Then whatever that area turns out to be, I'm going to have to add it to the integration of the orange. So again, just to give you a little bit of color coding here, this is going to be the yellow piece. And then this second piece here is going to be the orange piece. So I have to integrate this from 0 to 2 because those are the x bounds of the orange piece. And again, now you're just doing top minus bottom. So starting with negative x squared plus 2x minus the cubic, 3x cubed minus x squared minus 2x. And again, that should be dx'd as well. So again, before you integrate, you're going to go ahead and simplify each piece. So as I go ahead and try to simplify here, if I simplify the yellow region, so from negative 2 to 0, if I were to go ahead and distribute this minus and then combine my like terms, turns out that it actually turns out to be a nice simple 3x cubed minus 12x dx. Then if I go ahead and simplify the second piece by distributing the minus, I'm going to wind up with an integration from 0 to 2 of negative 3x cubed plus 12x dx. So then you're going to go ahead and calculate each of those integrations. So starting with the first piece here, if I integrate 3x cubed, that is going to become 3x to the fourth over 4 minus 12x squared over 2, which can be simplified to be just negative 6x squared. And I'm going to have to evaluate that from negative 2 to 0. If you want to just finish that piece all the way through, you can, or if you want to do the second integration. So this is going to wind up being negative 3x to the fourth over 4 plus 6x squared. And I'm going to evaluate that from 0 to 2. So again, just to reiterate, this here is going to give me the area of the yellow region. This here is going to give me the area of the orange region. So you would want to go ahead and calculate each of those different pieces. So if I go ahead and do the yellow piece, you're going to get a 0 minus, if you plug a negative 2 in for all those x's, you're going to wind up getting 0 minus negative 12. And again, this is going to be the yellow. Then you're going to add it to, if you wind up calculating the orange, you're going to wind up getting a value of 12 minus 0. And again, this is the orange piece. So if you calculate the yellow, you're going to get a 12. If you calculate the orange, you're going to get a 12. And if you wind up adding those together, you're going to get a final answer for the area between the two curves is 24. So if you take a look here, again, the 24 that you get in green there, that is what happens if you add up the orange to the yellow. And because you're trying to find the area between the curves, you do have to incorporate both pieces. So again, there would technically, I guess, be more thorough work that you would show for these. I would imagine that hopefully that is something that you could do on your own, since we're doing the more difficult piece with the graphing. And then here's the final problem of the day, and really kind of the last way that it might get more difficult. Well, that just means that the curves might be a little bit more unfamiliar. So we're reminding ourselves of the sine and the cosine here. So notice that you have the sine wave in red. Notice that you have the cosine wave in blue. Again, both of them have a period of 2 pi. You could graph them on your graphing calculator. You could use your unit circle, but here they are. If you were to continue to graph the sine and cosine, they actually intersect infinitely many times, whereas all the previous examples only intersected a finite number of points. Every time the sine and cosine intersect, they create a bounded region, and each of those bounded regions is going to have the same area. You're being asked to find the area of one of those regions. So if you're only being asked to find the area of one of those regions, my advice is to choose the first positive one. So I am talking about this region right here. So again, as I highlighted on mine, you should also highlight it on yours. Just to be clear, if I found the area of this bounded region in pink, it would wind up being exactly the same as the yellow, but just to make my life as easy as possible, I'm going to choose something that's all positive, and then smaller values. So notice that if I'm going to do that, I need to find those 2 points of intersection, which are of course given to you. Hopefully it stands to reason that throughout that region, the top curve is the red and the bottom curve is the blue. So as I go to set up my integration, again, for just that yellow piece, I'm going to be getting the integration from pi over 4 to 5 pi over 4. You're going to be doing the top curve. So the red curve is the sine minus the bottom curve, which is the cosine. And don't forget your dx. Then you have to integrate, and if you need to use your formula sheet, by all means. The integration of a sine is a negative cosine minus the integration of a cosine is just a regular sine, and you're going to evaluate that from pi over 4 to 5 pi over 4. So if I start by plugging in 5 pi over 4, that is going to give me the negative cosine of 5 pi over 4 minus the sine of 5 pi over 4. Then, fundamental theorem of calculus, you're always going to be doing the subtraction. So now I'm going to plug in pi over 4. If I plug in pi over 4, I'm going to get the negative cosine of pi over 4 minus the sine of pi over 4. To calculate farther from here, you would either have to use the graphing calculator in radian mode. Remember, if you're using pies, you're using radian mode. Or you can just remember what happens on the unit circle. These are all the pi over 4 family. So the pi over 4 family is root 2 over 2, root 2 over 2, and then it changes by quadrant. So we need pi over 4 and we need 5 pi over 4, and 5 pi over 4 is in quadrant 3, which would be the double negatives. So if I go ahead and sub those in, this becomes negative. The cosine of 5 pi over 4 is negative root 2 over 2. So a negative times a negative is going to cancel out to be a positive. Then minus the sine of 5 pi over 4 is negative root 2 over 2. So again, a negative is going to cancel, which is going to give me the following. Then minus, if I go ahead and do the negative cosine of pi over 4, that's going to be negative root 2 over 2 minus root 2 over 2. So if I add in the first set, root 2 over 2 plus root 2 over 2 is 2 root 2 over 2. And then minus negative 2 root 2 over 2. So minus a minus, of course, becomes a plus. So this actually becomes 4 root 2 over 2. You can then divide by 2, which is going to give you a final answer of 2 radical 2. And again, yes, you're welcome to give the decimal equivalent as well. So again, just to reiterate, this is the ordered pair in the first quadrant. This is the ordered pair in the third quadrant. It's always x comma y, cosine comma sine. Hopefully it hasn't been so long since you've done that. So for tonight's homework number 75, there are exactly 4 problems. They give you the graph. They show you the points of intersection. All you're trying to do is top minus bottom. If you need to, switch the top and the bottom at some point, then do so. So thanks very much for tuning in, guys, and we will catch you next time.